Welcome from Esther Huang and myself, Peter Papesh, for all of those who have joined us. We are expecting a few more as time goes on, so I'll just do some housekeeping notification. Please, everybody, and I'll repeat that, mute yourselves until the end of the session, under the end of the presentation by Henry and Bart and David Bliss. I have another housekeeping request. If you wish to self-report and get AIA credits, go to the chat room and join the link over there. You will find it. And you can self-report as long as you have your name and your AIA number for this session. You know the title of the session, which is a whole systems template for a carbon-free Boston. And I think with that, we've got as many people as usually come promptly, and then maybe some more. And I will repeat this admonition about getting AIA credits. In any case, welcome from Esther and myself. And let me introduce the three presenters today. Henry McLean, who you can see, is architect and educator. He is also AIA and lead AP. He has been actively promoting green design with civic and educational institutions in the Northeast since 1987. My God, he's that old. He has taught and developed curricula at the Boston Architectural College Sustainability Design Institute, and is the chair of the Milton Alternate Energy Committee, has helped the town of Milton secure DOER and federal green community funding. His work has been published in the Boston Globe, in Architecture Boston Magazine, and Preservation Magazine. Bart Bales, PE, MSME, is head of BEA. He is a registered professional engineer with a master's degree in mechanical engineering from the University of Massachusetts at Amherst. BEA is an energy and facility advisor for the Commonwealth of Massachusetts under a statewide contract, and as such is pre-approved to provide energy advisory service to any state and municipal entity in Massachusetts. That's very useful for those of us who are somehow involved with community sustainability projects. BEA is also a regular provider of utility-funded energy analyses and advises a number of towns and cities on green community projects. David Bliss, the third presenter, AIA lead AP, is a consulting architect focused on the design of building enclosures. With more than 25 years of experience in architectural design for new construction and rehabilitation projects for institutional and commercial projects, David now specializes in sustainability, preservation, and design of new and existing building enclosures. Over the last decade, he has broadened his background to encompass high-performance building design and related aspects of building science, climate change, and renewable energy. Now, be aware that we are recording this session, which will then be put on our website, I hope, or the link will be provided by Susan to this session, in case you have other colleagues who couldn't come, who would like to go and hear about the topic, which is, once again, a whole system template for a carbon-free Boston. And with that, Henry, you're on call.
All right. Everybody see that okay?
Yep.
Great.
Yep.
Oh, thank you, Peter and Esther, for inviting us in. I'm going to start this presentation along, and then Bart will pick up after me, and then David will follow him, and then we'll have some good time for conversation questions. So this is actually, we're all teaching together this semester for at the BAC, Boston Architectural College, a gateway program with about 10 students, which we started last week, and we're essentially testing a concept or a retrofit to Boston City Hall, which a number of us started going back about, well, 15 or 20 years. I actually taught a course in at Wentworth back in 96, which sort of began this effort. And we ended up presenting that to Mike Galvin and his team at Property Management back then. They provided a lot of data, which we analyzed, and we ended up presenting that to the mayor's cabinet back in 97. And then about fast forward 10 years, we presented with a bunch of other folks to help, the challenge was basically thinking about Boston City Hall, which there it is right in the center. Coming down, Mayor Menino, our ex-mayor, had considered that possibility. And so a bunch of people interested in preservation, Dakamomo, and a bunch of people, included us, who were interested in energy retrofit of the building, came together and had a hearing at Boston City Council with Michael Flaherty, and we'll present some slides that we shared there. So this has been sort of a long-term effort that we're excited to take to another level with this gateway program, and David and Bart will talk a lot more about the specifics. But I'm just giving you a background, and this is, of course, the old spot where Boston got started. It's been the same centroid to Boston through all these years. And we're basically looking at going from a population of 16,000 to 22.5 million in whatever it is, 200 years, 225 years. And of course, we're all aware of what the downside of climate crisis is, looking at for Boston with a storm surge. Here we see 7 feet, 14 feet, and of course, these were the unbelievable concept of Boston becoming an island again. So that we were an island, and we've been filled in, and back to the idea of being an island again. So forestalling that means taking action in all of our buildings. 2/3 of the carbon coming from downtown Boston coming from buildings, and 85% of the buildings that are here now are going to be here in 2050. And so the challenge is, how do we do that, and how do we take a building like City Hall and make that change? Of course, City Hall is on this wonderful historic pathway in Boston, the walkway to the sea. It's at the hub of culture. This is the architectural record that came out in February 1969. Hard to believe, a year after MLK and RFK were killed, this building was born. And with it, a whole new appreciation and understanding for this central civic area of Boston. So we've been thinking about this idea of a green beacon. Jerry Ives and Francesca Amaker and Ambrose Spencer, a bunch of other folks who've been working on, have been part of our effort that got started way back when, and a lot of people who've been on this project have since retired, and but we'll talk more about that. So this is the idea of what is a net zero energy building, generating as much energy as it needs on a site energy annual basis. But also a more common definition is an energy efficient building where on a source energy annual basis, the actual energy, annual delivered energy is less than or equal to the on-site renewable exported energy. And we'll get into this a little bit more and come back to this whole concept, but the idea is that we want to cut the load of this and really do a deep energy retrofit on Boston City Hall, and then make up the difference with municipal aggregated green energy. This is the original site plan, and of course, you all may be familiar that the plaza is now undergoing the beginnings of a major renovation with Sasaki and Associates, and I just put this in here because it's the original concept of a bridge. It almost looks like a wide road going over Congress Street to Faneuil Hall, which is here. And I just took a picture of the new wonderful bridge over in on the Fens, which might be an idea about linking this together, maybe another extension of that. Of course, we have the reclaimed pedestrian urban habitat of the central artery, which has been a massive reconnection for City Hall, going back to this picture just quickly. For those of you who don't know Boston, the artery was right here, and now it's really connected to the sea in a way and to Faneuil Hall. Right, the artery is actually down here further. But so that's gone, and we have this wonderful new connection. So what we're considering is reducing the energy consumption, helping to become a more inviting, accessible space, and while preserving the landmark quality of the building. And this involves leadership, this involves integrating whole systems approach, the Living Building Challenge, we'll be talking about that. And then, again, this is more background on the history of this project, which you can go to the BASE site on and find out a lot more about what we've been doing over the years. So the major concept, the first design goal, was to make the building more energy efficient, drastically reduce the exposed surface area and cut the operational energy, and essentially capping this donut on stilts, which is one easy way of describing this. The building has got a major amount of openings, and this is the concept of creating that cap and reclaiming this with new sidewalls that would come down. Here's the original plan. The fourth level has the most square footage available, probably close to 30,000 square feet on this floor plate alone. Each floor plate of the building is about an acre. These are the sections which give you an idea of how wide open it is. Really, the upper floors just sort of float over this lower section, which is this potential zone that we want to reconnect and reclaim, essentially. So these were some original plans, or some updated plans that Francesca Amaker and I worked on years back. This is a lot of the slides that we presented in 2008 to the City Council. And the third level, which most of you are familiar with, is where you enter in. We were talking about connecting with this bridge across Congress Street and bringing people right into the building, having them be able to come through in a new set of escalators that would go up to this fourth plan, sorry, right here. And those are the escalators in this new enclosed atrium. And then these yellow zones would be reclaimed from the outside of the building. Currently, they're just sort of hollow exterior spaces. We talked about a sustainability center for the city of Boston that might be located in this. There's been other concepts that have been put forward we'll talk about in a minute. And then up on the fifth floor, we can reclaim a bunch of square feet here. Again, without sacrificing the sort of heritage aspects of the building. And then the roof. We talked about the possibility of a green roof and reclaiming maybe another 20, 30,000 square feet up there for a restaurant, conference center. This is post-COVID years, of course. This is a look at the roof right now. You already have these massive mechanical penthouses, which we would essentially enclose and connect. There are two massive open wells, if you don't know the building, that sit on the, this is more the south side. This is east over here, west here, and then north on this side. And then in the central atrium, so the idea of connecting those was something that we'll talk about in a little bit. Here's a bird's eye view. There's those two atrium spots there, mechanical here, open well. And this idea of a new, access point to the roof from Faneuil Hall Marketplace that would be connected by this bridge and this sort of side ramp here. And then again, reglazing and re-enclosing all that added space. Quite a difference from what's there right now. And these are the two pictures at this corner as we have it now. Another shot, another concept of this was to open up the existing parking on the base floor, which is behind this wall here, and then punching holes for all these office spaces which have skylights, but the skylights are pretty much not letting any light in anymore. And these are all pretty, all day, no daylight at all in any of these office spaces right now. Regreening the base, more windows on the plaza side we talked about. Here's an earlier sketch of what that would be like here. And then picking up on different precedents from a variety of different places of, how do you green that base and soften the building's exterior? Just a quick concept of, reclaiming this energy. We'll talk more about the mechanicals. The mechanical space is really right up here, and then that would allow for this downward movement, interior stairways potentially for some of these wonderful open atria. Precedents, the NMB or ING Bank in Amsterdam. We'll talk more about that with David, and then ideas of shading the skylights. Some of these could be operable, driven by PV. The city is looking into a 40 kW PV system up on the roof now, so there is some solar access that's going to be available. And mechanical, again, the work from the outside in, optimize the envelope first. We'll talk about that. Then lighting, then redesign the delivery system, and then the equipment. And just gives you a little bit more of the square footage of that area, and then what that comes out to in terms of 1.75 million cubic feet. So it's a lot of space in there. Here's a picture of when it was being built, late 60s, so this is probably 67, 68. Notice the car vintages and these elements of these exterior stanchions that essentially go right through the window wall system. So this is one of the problems. It's just telegraphing energy. It's really built as a radiator. And it's a wonderful little chat. So these are some of the numbers that we came up with, well, really over time. When we did our original analysis at Wentworth, we came up with a EUI of about 270 kBTU per square foot per year. In the 2000 to 2008, we found the reported energy use was about 148, 150. This is, again, the embodied energy. We looked at the number of BTUs to actually make the building. And then our proposal in 2008, working with Mark Kelly, engineer, and we got it down to about 38 or 40, and we'll talk more about that in a second. And then right now, with the updated numbers that we've gotten from the folks at Property Management, it's operating about 110 kBTU, and we think with updates, and Bart will talk about this in a second, that we can get it down to maybe 27, potentially with a new borehole field on the plaza as well. Some of the numbers of how this would happen, the original construction costs were updated for 2019 numbers. We had 2008 numbers we've updated 2019, and we were looking at maybe a $68 million project, 490 bucks a square foot, 130,000 reclaimed square footage. The insulation, engineering, soft costs, insurance bond, et cetera, brings it up to about 83 million. And then when we look at the energy savings, which we think is going to be about, the number we ran is about 1.3 back in 2008 with a factor of 1.2. In that time difference, we think we can get that up to about 1.6. The avoided rental, the income from the other rental spaces, so it's about a $10 million annual recoup, and divide that into the budget, you're looking at about a less than 8-year payback. These are some of the slides from Mark Kelly. We'll just go through it. This is his analysis from the beginning of this building is just wide open to the winds. There is no top, essentially. And we'll run through this a little bit more later, but we were up around 150 back there. And with the best case, he said we can get it down to about 32. And we did a preliminary analysis and heat loss and whatnot. We're in the process of getting more data. We're working with the municipal energy unit, David Musselman at the city right now, and John Sinagra from property management. And we're going to follow up on all this data. And that's really the focus of this course that we're running at the BAC for the next year. So again, what's the best measure package that Mark ran? We'll talk more about this with Bart, but basically we would be adding about an inch of urethane or some kind of insulation on the outside to get up to about an R10, and optimizing the envelope, then the lighting. We're going to be getting into all this, so I won't go too much more on that. I just want to show you a few more precedents here, that, and these are some of the boards from Francesca Amaker, Boston Public Library. We'll talk a little bit more about that. David's got a lot of experience with the BPL. Some of the other ideas are bringing wood and concrete and brick to in a more fun level to bring up the level of the interiors at the City Hall. New atrium, that there's many options at Copley Plaza for options of precedents that we've been looking at. The Genzyme over here in Cambridge, shared light coming through the music building at Yale, bringing in art and water, or an idea of biofilters and healthy airs, and in creating these interior atria that really have a vibrancy, is what we'll be looking at as well. And finally, just some of the challenges that, we're excited to be looking at this Living Building Challenge and how they're partnering with the WELL building standard. So that's something that we're going to get into in depth. Of course, we have this whole new issue with COVID area of ventilation, and the building really does have, there was some history of sick building syndrome reported back in the early 2000s. But, basically it needs a lot of work on that level as well. And Bart will talk more about that as well. Some of the other resources that we're taking advantage of, the Rethink City Hall, Boston City Hall and Plaza study that was done in 2016 with UTIL in the city. They focused in on the optimized civic center here. We also wanted to note that there was a discussion of the glass over the central courtyard space and infill exterior openings on 3, 4, and 5. So that has been discussed and thought through at that level. It's a wonderful document that we're going to be getting into in depth. We're also looking at the carbon-free Boston study, which gives you an idea of what we're using for 1 million square feet right now in the city and what we're going to add between now and 2050 and how that translates to building emissions. As I mentioned earlier, we're going to be really looking in depth about how the energy now is broken down in City Hall, plug load, ventilation, lighting, cooling, water heating, and space heating as part of our analysis. We're also looking into the Super Studio, the new Green Deal Super Studio. Many of you may know about it. I believe this is still open. The Landscape Architecture Foundation is running. We have this green roof that we're going to be talking about in the edges of the plaza. We're also building on the work that Michael Williams and his team did. They did a gateway program back in 2014, looking just at the atrium itself and turning that into a new museum for Boston called Boston 360. And he had an article in the Globe, a little bit before that, back in 2013. So that would be one resource. So I'm going to hand it over to Bart. This is a picture of us up on the roof a couple of weeks ago with John Sinagra, and this is the size of that mechanical system up there to give you an idea of it. There's David, and this is one of those window wells. It's the top light shaft for single pane glass for that massive stack effect. So Bart, let me go to you. I think this is it.
Henry, let me just jump in before getting to Bart to remind everybody that if you go to chat, you can get a link to the AIA self-reporting system, and you can do this on your own after this session. But you can, it's beneficial for everybody to hear that. Also, I heard some noise, but somebody turned off their sound system. Again, let me request that you put yourselves on mute until the end of the presentation when we'll open it all up for Q&A. Now, Bart, you're on. Thank you for coming.
Very good. Okay, I'm from Bales Energy Associates, and appreciate the introduction. And so we can move on past the slides about me to just giving you a top view from the roof of this atria area. You can see that it's quite large, and there's a lot of flat roof around this area. So move forward. We can see that there's a lot of open roof here, and those raised areas that run on the roof, those are not just walkways, those are actually ducts and mechanical related chase areas and that kind of thing. Can you go back to the slide, please?
Sorry.
And this space is there's going to be a lot of different competitions for this space. Much of this space is not going to be viewable from anywhere from the ground, so it is potentially usable. This is for the green roof idea, would be part of this. This is also where some HVAC equipment could be located if we're doing heat pumps. And this is also where solar could be located, and there's more space than I show here. Go ahead. There are large air handlers that blow large quantities of air around. There are 20 air handlers serving the building. These are up in the top, the ones shown are in the top of the, on the penthouse. Next. The HVAC system, if you look at the top of the building, you will see those ducts moving laterally out to the parapet, and then they are going down in the outside of the parapet down through the building. Going back up to the parapet wall is solid concrete, and there are pieces of equipment behind that concrete that need maintenance, and that was not a very well thought out thing, and so openings had to be made to get to those. We can see that this is a complex way to go given the way the building's surface moves downward and inward at some locations. So next slide. This is not an Escher drawing. It does look like one. This is a representation of the ceiling structure, and then you can see the return ducts and everything that you were seeing from above. I mean, from the side, is that same layout. So it's very unusual.
There's those pipes right here coming up and down through the thing here. There's the parapet right there. Yeah.
Yeah. Okay. Next slide. And this is just one floor of the building, and what you can see is that there are individual AC units serving many spaces. These units, there's been problems with the distribution, as I was mentioning, in the parapets, getting down to these areas and having to move water and air down to these units. I'll give you a clue that we're considering replacing these with heat pumps located probably in the roof grid, the ceiling grid, and then just delivering air for ventilation through the existing ductwork. or through adjustments to that ductwork. Next.
Just to add one thought there, Bart, this is the, all the mechanical is located at the level of Faneuil Hall, which is very low. So it's a resilience issue we'll be talking about as well.
Right, we'll be seeing that in a few more pictures. Just showing that the building was designed for an open office design. And then as they moved along, go to the next slide. In some places they enclosed the open office design, and that was not always done in a way that related well to the existing HVAC system, where you didn't have individualized control in individual spaces, because the spaces were designed without regard to where the HVAC was. Go to the next slide. This is just a typical perimeter unit. This blows air out and is got heating and cooling coil in there. Next. Another delivery terminal unit, typical unit. This is the kind of unit that we might be replacing with a heat pump head and with condenser capacity somewhere else, which might be borehole related, or it might be condensers located on the roof. Okay, next. This is the chiller with a newer chiller. Move to the next. And here's the older chiller. These are located down in the basement or down in the base floor. So this area could be flooded with storm surge. So that's a concern given the resiliency issues of climate change. Next. Just showing that they have both high and low pressure steam delivered to the building, at least the original design they did. The person taking us around indicated that they were operating all on low pressure steam. Now, we haven't independently verified that, but that's what we were told. And they're using steam to be converted to make hot water, for hot water being distributed around the building, and then the chillers provide chilled water for going around the building. And this steam is from a district steam sent from elsewhere. It's not made in the building. Okay. One thing to note about the district steam is that it's not clear in the energy metrics that we're seeing how the steam is being treated, whether it's being treated as an energy input, or whether it's being considered as free energy and not being considered as an energy input. It of course should be considered as an energy input, because it is something that requires energy to make, even if it's part of a cogeneration plant, combined heat and power plant. This is how the hot water is made. It's a plate and frame heat exchanger, and then a domestic hot water is sent around the building. Okay. And here is the light well that was being mentioned. You can see how high it goes. We're looking up at it. And this is a destratification challenge with such a high ceiling. Next slide. Similarly, in other areas, there are very high ceilings at times. Go ahead.
Okay, that's the other one.
Okay, you jump to slide.
Sorry.
Okay, so it's really important that we look at this, think about this building as a whole. We think about optimizing the enclosure to the extent that we can. The predominant enclosure improvement we're trying to do is to enclose all those Tetris-like cutout holes in the building and covering them with a common surface, so that we're rendering this building not visually necessarily, but effectively more like a cube shape rather than a shape with massive surface area with, so we need to think about the whole building, to how we can reduce the loads to the extent we can, and how we reduce the lighting loads, and then how we reduce how we deliver the energy that is going to meet the loads. So next, so two key technologies that are going to be in our toolbox to make things a lot more efficient is our energy recovery ventilators, or energy recovery, and air source heat pumps or ground source heat pumps. I'll talk more about each of these. Next. Okay, this is of course only a residential application, but the principle's the same. You're bringing air, you're intentionally bringing air to all areas of the building for ventilation, which is for proper health. And then you're exhausting the same amount of air intentionally, otherwise having a very tight structure. And you're recovering the thermal energy that's leaving the building and preheating the air coming into the building. Next slide. The most effective kind of heat exchanger is counterflow, where things run opposite to each other. Counterflow heat exchangers can get on the order of 85 to 90% efficiency, which has some very useful impacts. You can see that the temperature difference between the temperature going out of a space and coming into the space is only 4 degrees there. It's 68 going out and 64 coming in. So it's not going to chill the space much, and you may be able to deliver it without tempering if you deliver it in the right location. Go ahead. This is just showing you how that system works. It's counterflow through the middle of that hexagonal shape, and that gets maximum heat recovery. Go ahead. So typically you have rooftop units or air handlers that are delivering air into the space, and then they're pulling air out of the space. I mean, they're returning some air out of the space, maybe exhausting some air at the rooftop unit, and then there's also independent exhausts like fan exhaust that are letting air go out. You can see by this methodology, this design, you have no heat recovery going on. You're losing the thermal energy in the air going out of the building, and that therefore the air coming in needs more energy to be heated up to temperature. Okay. And this is just showing that if you have a dedicated outside air system, you are delivering the air without connecting it to a air handler, and you're not using it for heating and cooling. You're using it just to deliver the ventilation air. And what we're finding is decoupling ventilation air from heating, even if it's air for heating and cooling, gives us a bunch of advantages. So next slide. This is just showing us a multi-zone dedicated outside air unit. Next slide. So look at what we're talking about doing. Here's on the top is a rooftop air handler, and we're thinking about replacing it with what's on the lower picture. So the item on the left is a heat pump condenser. The item on the right, if you could point at them, Henry, it'd be great. Bottom picture. The item at the right is the heat recovery ventilation unit. The item on the left is the heat pump condenser unit. Next slide. So one of the things that if you're segregating the ventilation, you you can demand control it. You can have a CO2 sensor that will allow you to estimate how many people are in the space, and by estimating how many people are in the space, you can dial up or dial down the amount of ventilation to match the amount that is required for that occupancy. And this can result in very significant savings because many spaces may be only occupied some of the time. Next slide. And you can do the same thing for a multi-zone system as long as you have sensors in each space. You can accomplish the same kind of effect. Next slide. One of the advantages that I was mentioning to using higher efficiency heat recovery is the temperatures that result for the higher performance one. Notice that on the left-hand side, the typical counterflow heat exchangers that many are more typical heat recovery ventilation systems only bring the temperature back up a certain amount. And at 40 degrees outside air temperature, you'd be bringing air in at almost at little less than 60 degrees, where with the cross-flow heat exchanger, you'd be bringing it in at almost 66 degrees, which is very close to the temperature. And that's also the room temperature. Notice that there's a significant difference in the amount of energy saved in doing this as well. Next. Okay, so the other tool in our toolbox is the air source heat pump. And there are many manufacturers now. Most of them are Asian, Japanese, or Asian companies that have developed these cold climate heat pumps that can work down to minus 15 degrees, can maintain their capacity down to 5 degrees, and they use modern variable speed drives to increase their capacity as the temperature gets colder. It gets harder and harder for a heat pump to do its work the colder it is outside, because we're drawing the energy from the outdoors. And the reason we call these air source heat pumps or ground source heat pumps renewable thermal systems is that they can be driven by renewably generated electricity. That's one reason. And the other reason is that a large percentage of the energy that we are moving into the space is coming from somewhere that we're not paying for. It's coming from either the atmosphere or from the ground. Next slide. So this drawing is just shown to show you that you have to have something outside and you have to have something inside. The blue is the outside coil. The red is the inside coil. Now we're used to calling things like this condensers in air conditioning, but the outside coil is a condenser when we're doing air conditioning, but it is an evaporator when we're doing heating. So, and all that happens is that the flow is reversed in these systems to accomplish both heating and cooling. You can see that a key element that was left out of the other drawing is this little expansion valve, which drops the pressure down and lets the magic of the heat pump cycle work. Energy is, in heating, energy is drawn from the ground or the water. That's the blue on the left. And then the fluid moves toward the compressor. The compressor increases the pressure, that increases the temperature and it adds some energy to the fluid as well. And now it's hot enough that heat can transfer from the condenser to the space, and then it goes back through the valve, and the cycle just repeats. It counts on a lot of, go back please. This counts on the evaporator side. It counts for a lot of free air to move past this coil. So it's very important to leave free space around condensers. You can't enclose them. You can't put pretty things around them unless you do it from a good distance so that there is good air movement. So next slide. Now the magic of the heat pump is you pay for the 1 unit of electricity, the yellow there, and you get 2 units of energy out of the environment or out of the ground. And that adds up to 3 units getting into the house. So that means, what's the efficiency of that? What's the efficiency? We're used to taking efficiency and saying energy in divided by, energy out divided by energy in is normally what efficiency is. So if we take energy out divided by energy in, 3 divided by 1 is 3, so that's 300% efficiency. So we don't call this efficiency, we call it coefficient of performance, because we don't like efficiencies that are over 100%. And the reason it's not really over 100% efficient, it is delivering more energy, but the key is that in this case, 2 of the units aren't being paid for. They're coming from the environment. Next slide. So what do indoor units look like? They look like all sorts of things. If you go from top to bottom, from bottom to top, the unit at the bottom would fit up in a T-bar ceiling and would blow air out the sides and draw air in the middle. The unit, the MLX-KA that you see there, that's a ducted, a unit that blows air out and is ducted. There's a unit, the MFZ-KA is a floor-mounted unit, and the MSZ-FD is a wall-mounted unit. And there also are air handler versions of this kind of thing that aren't shown here. So they're quite large air handlers that can move air through traditional ducted systems. And these are still heat pump heads that can have the high efficiencies that we're talking about. Next slide. What do the outdoor units look like? Well, here's outside of a library, some large units. This is the size units that we might expect to see in clusters on the roof. And these are condensers when it's air conditioning, and they are evaporators when they're heating. So next slide. Just to show, you can have these heat pump heads spread all over the place in the building, the black boxes. And something that you may not be aware of is with something called variable refrigerant flow systems, you can have some of these units delivering heating and some of them delivering cooling at the same time, even though they're hooked to the same condensers. And that adds some added efficiency savings. It's in effect transferring energy from the overheated space to the space that needs heat. Okay, borehole technology, there's been talk about doing ground source things out under the plaza somewhere. That means you drill boreholes down into the ground, and they typically be 300 to 500 feet deep. And then you run run water down into the ground and back up, and then you use the heat pump to take energy from the water. The water that you're getting from the ground might be 45 degrees, but the heat pump essentially allows you to upgrade that to temperatures that are usable for heating a building, things up to 120 degrees. This slide, I don't want you to think about the standing column here. We would not be wanting to do standing column wells. We would want to be doing closed loop wells. But other than that, the look of this is similar to what we would have with a closed loop multi borehole system, that you'd have pipe going in and a pipe coming out of each of those boreholes, and then going back to the water-to-water heat pump units that we might be using inside. You can also have water-cooled units that would serve units like the heads that I showed you, the various terminal units, and those could be so it could be water to refrigerant heat transfer, and Mitsubishi has this technology, as I expect some of the other manufacturers do too. Next slide. So if you combine heat recovery with heat pumps, suddenly you've got this extra savings that is due to looking at things in a systems basis. And that's where we're reducing the energy required to blow air around the building, because we're blowing only the amount that needs to be for ventilation. And we're delivering the thermal energy and the cooling with heat pumps located in each location. And that automatically gives you individualized control in each area for each heat pump, which gives you very good control. And this approach also would help us to deliver more net air for ventilation purposes, and might fix some of the health and discomfort issues that may exist. Next slide. So here's the kinds of things that can happen. Can be very big savings, sometimes 50% savings by this combined approach. And actually compared to depending on what kind of system you're going against, it could be more than that, because the heat pumps themselves will save two-thirds roughly of the energy input required for heating and cooling. Okay.
Art, I need to alert you. You've got about 2 minutes because we're running close to the wards.
Yeah, we're done. We're done. Essentially, I just wanted to show that last picture. If you can go back to that.
Yes.
There's what it might look like on top of the building.
Oh.
So that could be inset so that it was not able to be seen from below. Go ahead.
Just want to move on to David. Sorry, David.
Okay. Once more, let me just alert everybody. First of all, we've got a very large crowd attending today. Please go and look at the chat box where you can find a link for self-reporting to the AIA. And with that, let me hand over to David. Thank you, Bart. And Henry, I assume you're going to stay on.
Yeah.
As sort of guide. Bart, David. Hello,
Thanks,
David.
Peter. And thanks to Bart and Henry for introducing me in this project that Henry's been working on the longest. And also want to take a minute just to acknowledge the Boston Architectural College. It's one of the colleges that I graduated from, and the most recent one that I graduated from. I started out in engineering and ended up in architecture. So all that kind of informs the way I approach projects. Let's start into the slides, Henry.
Yep.
So we first met with our group of students last Friday, and we have about 9 or 10 involved right now. And I was very impressed with the diversity of the group that we had and the diversity of where they were coming from, because we had people from the Middle East and from California and New York, as well as more locally in the Boston area. But it was really interesting to see so many people from so many cultures getting involved in architecture.
These are bachelor's and master's students, but most of them are master's students in the class. So it's a good group.
Yeah, it's going to be a great class. So this is one of a few slides that I used in our introduction to the students, just to kind of put it on the table, what we're going to be getting into over the course of the semester: the systems, the 4 barriers, materials that are both existing and potentially new materials, and trying to understand what those materials are capable of, and finally the details and transitions that you would need to work out as part of any real project. Let me also add that we're trying to set this up to run as a real project with a client, the city of Boston. Representatives are going to be coming in, and various consultants coming in. Next slide, Henry. So one way to look at this is that it's a barrier wall retrofit. Barrier wall, as you may know, is not a cavity wall, but it exists to repel the air and water on the outside and keep the inside dry. And this building is also complicated in a way that, geometrically complicated in a way that makes that task very difficult. And this photo on the left kind of illustrates that. You've got some steel curtain wall, I believe it's steel curtain wall, that's mashing into what I believe to be a veneer over cast concrete structure of brick and plain concrete. And up above, we've got these soffit areas that, as Henry mentioned, go essentially through the building. So you have an incredible heat loss on the building enclosure. And the real challenge for us is how to insulate that in a way that meets minimally the building code that we have today, which for a mass building would be about R13. But in order to really get close to net zero, we have to tremendously improve that. And so it remains to be seen exactly how that's going to be done. There's a combination of problems that we have to address with how it could physically be done, but also the aesthetics of it, this being a not quite a landmark building, but on its way. Next slide. Started by looking at a few different barrier wall retrofits that one of which I'd been recently involved with as a building enclosure commissioning agent on the project on the left. You see a before and after. That's the Holyoke Community College and the campus center there. And they put basically cladding on the outside of the building, enclosing it with curtain wall and metal panel. On the right side is the Smith Campus Center at Harvard, right in the center of Harvard Square. used to be called Holyoke Center. And they've recently done a retrofit of the building, and they replaced a lot of the cladding, opened it up with more glass, and they also used some additions that they did more or less in glass as floating elements to let lots of light in. Next slide. The second part of my responsibilities with this project are with the heritage, historic preservation of the City Hall. And so I'm beginning to dig into the architectural history, whether it's actually not yet a landmark structure, and that part of that is probably that the owner might be reluctant to make it a landmark. So we'll see where that's going to be going. We're trying to get our hands on original drawings so we can look at the details and understand what the window systems are and how they are attached. Precedent studies, looking at exterior, interior spaces, and other precedent studies on energy efficiency. And then we'll be making the pitch. Next slide. So as a precursor, just looking at how the National Park Service has a series of preservation briefs that how they recommend dealing with historic buildings or additions to historic buildings. And by and large, this document is set up as it's really an addition. So they're looking at making it very contextual, yet separating it. In our case, we're doing additions to the building, but they're integrated within the building. And that's going to be tremendously difficult. Next slide. Other precedents that we're looking at is the ING Bank building in Amsterdam, which is, I think it's 90s. Henry, is that correct? I think in the 90s it was put in.
86, 90, yeah.
Yeah, so it was actually at the time a very, very efficient building and has a series of light wells that come down, and looking at the light wells that exist in the City Hall today, when I saw this, I began to think it in a different way, that those light wells could also be canvases for artists. In this case, this is a reflective metal and that's been placed and is reflecting light further down into the space. And they have, it's just an opportunity that is one thing that could happen at the Boston City Hall. Another precedent on the left is the Johnson Building at the Boston Public Library, which in the top picture of it was as originally constructed. There were granite panels that separated kind of outdoor reading spaces for the reading rooms behind. And so they created a little enclave, if you will, that was tried to avoid all the street traffic and stuff. But it also created a very harsh approach to the building. This is actually a brutalist building. No other way to put it. It's a modern brutalist building. So recently at the library, they removed those granite panels and replaced the wall panels that were behind it with curtain wall, and they've updated the interior, and you can see it's a lot more lively to the exterior and warm on the interior. Next slide. And of course, we're going to need to make a pitch. We're going to need to make a pitch that, as was put, maybe it was 10 years ago, the greenest building is one that's already built. That was a National Heritage study that was done on existing buildings, and they found that existing buildings could be retrofitted and upgraded to reduce energy on a really large scale. And also the 2019 Climate Action Plan, if you look carefully down the lower right-hand corner, it says preserving Boston history, and you link that, and that goes to the Landmarks Society, Boston Landmarks Commission, and the photograph in the background is Boston City Hall. So we'll be trying to make our pitch to our client, the City of Boston. Next slide. So the third and last piece I wanted to mention was project management. And as I said up front, it was thought that we would run this studio as kind of a architectural practice would, with consultants, client, us as team leaders, and a work plan and schedule. Next slide. So the reason I got selected to do this is because I've done it once before with the McKim building at the Boston Public Library. I was involved in the last 3 of 4 phases that for the restoration of the McKim building. I'm not sure that they ever completed the restoration on the upper level, but I was involved in a very complicated project with multiple consultants, with owner representatives, with owners, with a client that lived in the building, and with multiple consultants ranging from fine art to lighting to stone preservation. It was incredibly wonderful experience to be on that project. And we hope that the students in our project come away with the same feeling about this Gateway project. Next slide. And so now I'll open it up for any discussion or questions that people may have.
All right. Let me just jump in before we get to that once more. First of all, thank you all for attending. It's a very impressive group of people that had the good fortune of hearing this very impressive presentation. Congratulations. You guys are have a lot to say. And now I'd like to go and open it up. I know Francisca has something to ask right now.
Yes. Let me just say, Francesca is one of the people that's been working on this project for many, many years. And some of her slides were in there. I think I mentioned them before. And I didn't see you enter early, but good to see you.
Good to see you. Yeah, I'm happy with this presentation. There are a lot of good things, especially good new things from Bale and David. Anyhow, I just recently stopped working on this because of other work, but I did want to just mention, and you might have mentioned that also, but David, please mention it. This is, you know, an architecturally quite important building, and so I have been a student of McKinnell and Coleman, and so I felt like very strong respect for this award-winning building when we did our original design, and in particular, you know, how the facade was treated. So the things that we did kind of were trying to be in the style of the original design. And but of course, this makes the redesign in terms of the envelope extremely difficult. And so, you know, there have been other proposals for City Hall which made whole envelopes over the facade, but I personally felt it was important to keep it And the other comment is that the roof, the existing roof, really needs a big volume to go over it to facilitate the air circulation, heat recovery, ventilation through the two different current courtyards or what air shafts. So that is a big opportunity for this added space. And when we designed it, we were paying a lot of attention that this volume wouldn't dominate so much. So like some of the recent buildings like Zaha Hadid did, where she designed something huge on top, we had been more respectful of the current City Hall facade, but perhaps that was maybe too respectful because it could be quite an interesting contrast.
Thank you very much, Francesca. All right. Any other comments and questions?
But just to mention one thing, Francesca, we're going to, I think with the students, we're seeing our efforts in the past as a test case, and we're going to run variations on that and look at, you know, options for not including the roof probably. But we obviously, the whole idea is to test it out and to see, you know, the advantages or disadvantages, and certainly getting feedback from people at the city, which we'll be doing as well. But that's a really good point. And for those of you who may remember, there was an architectural Boston issue Elizabeth Pageant ran, I think, years back, where there were a lot of, you know, intense introductions of forms coming through and over and breaking through City Hall in ways that aren't all that respectful for the work that Francesca just mentioned, that the original design. And Gary Wolf is one of the many people that we'll be bringing in, hopefully for some more feedback to the students in terms of his great work in the preservation Docomomo and the work that they did in showing the original drawings, which like the show was done several years ago at the BSA and at Wentworth before that. So we're definitely going to be engaged.
Thanks. Let's be aware. It's we're at 1:15. I want to be sure that everybody who has questions gets a chance, but please keep it down to a minute or so that the answers can also take up the 2 minutes. That means that we've got 15 minutes left, or unless other people want to stay on. So, next question, please. Hey. Nobody wants to ask any question. Let me ask this. Who is the client?
Well, the client is the city. We're working directly with the Municipal Energy Unit, which is tasked with managing the energy utilization of all of the city-owned buildings. Okay. David Musselman. We're also working with property management. And there's some architects and building engineers who are managing the building. So,
are you at the BAC lecturing? In essence, would you be doing more of this over the course of a semester, or are you? Is there a lot of research being asked of the students?
Yeah, so we're running what's called a gateway program. The gateway program was set up to give work experience and work credit to students who may not have had the opportunity to work in offices. It's also used as a tool to help nonprofits and municipalities in on projects of their you know, interest. So it's a wonderful opportunity to give both the city some feedback, give the students an opportunity to do research. And yes, it's a weekly class. We're meeting, it's a year-long commitment that we have now. We're doing it in 2 semesters. And we meet on Fridays for 3 hours, and we have reviews, a midterm and a final that we have, and lots of work. The students each spend about 20 hours a week in this program. So it's a lot of work.
It's a most impressive presentation. I think all three of you need to be congratulated. Anybody else? They're all blown away, and
Well,
rightly so. Okay, one more: heat exchangers and COVID-19. Let's. Are you, Bart? Are you addressing this at this stage, or is it still a work in progress?
I would say that that's still a work in progress.
Okay.
We're just starting. The net effect of the kind of approach we're talking about, though, will be to enhance the ventilation capacity of the building. If we do the approach I talked about of utilizing the existing duct runs, or at least the run areas, as just for ventilation air. They'll be oversized, of course, but that would allow us to deliver more air and withdraw more air, which might help if we can exhaust more air.
Yes, let's make sure that at least this group here understands that COVID-19 is primarily airborne. It's like tuberculosis. It gets transmitted primarily via airborne particles, and the better the ventilation, in other words, the more air exchanges that can be introduced into a space, the fewer the remaining parts of the cloud of contaminants that's floating around, thereby affecting everybody who's in the spaces. So they just keep that in mind whenever you get feedback. Hey, we can't afford this much. Bart?
Just
Yep.
one thing. We don't necessarily want to do just air quantities. We want to do filtration.
Yep.
For return air filtration, because we don't want to create other problems with the building by overventilating. You can get major humidity issues if you overventilate.
Okay.
And so we got to be careful.
Okay.
it's also, just to mention, there's the building right now is, with COVID, is 20% occupied. So ordinarily there's about 2,000 people that work in City Hall. Right now there's about 400. So there's a skeleton crew, essentially, essential services managing it, and they're on a 3-day work week. Yeah.
Well, are you actually planning for a number that the city has projected going forward? Is it going to be full occupancy, or is it going to be reduced occupancy of 400? I mean, that doesn't.
No. We're assuming that we're all going to get a vaccine at some point, and we'll be back to normal. I don't see the city adding, thinking even about this kind of massive expansion until we've managed the virus. But the other issue, and I just mentioned it, back in the early 2000s, and Francesco remembered this, there was an article when we were doing our research way back when, and I think in the days of our Wentworth study back in the 90s, where there was a Herald article talking about some employees at the city complaining about sick building syndrome.
Yeah.
So we know that it's not the healthiest of buildings right now, and not just the air, but the light, and that's another big part of it.
Yeah, one of the problems with the building is actually also the maintenance budget.
Yeah.
So for many years they would replace light fixtures with different color light fixtures and not check the mechanical systems other than do emergency repairs. So the whole mechanical system was a disaster.
Yeah.
Well,
there's also a report, if you go on Wikipedia and look up City Hall, you'll see that it's a report that it never got the funding for the maintenance that, for instance, Boston Public Library did. So, and David, I can correct me, but they've spent about, 90 to 100 million on the inside of that building over the course of those It's a lot of money.
Yeah, it's a lot of money. I don't recall exactly. But something like that. And then there's also now the Johnson building that also just underwent probably a 30 or $40 million project. There is a question on the chat line. What are we proposing for electric lighting?
I can answer that. The lighting, I've been surprised to see, has largely not been converted yet to LED lighting. So we would be looking at LED lighting to reduce the lighting budget even further. Right now, it's fluorescence, mostly 4-foot, what they call T8 fluorescence with electronic ballast, and we can do better with another level better with LEDs, and they'll also last a long time. So that's probably where we'll go. Jeff, does that answer your question? Jeff Berg?
We can't hear you, Jeff, but by the way, it's good to see you. It's been many years. You got to turn on your mic if you can. We can hear you. There you are.
Yeah, I figured you would do a conversion like that. I was wondering if you got into the details whether you're going to do lamp retrofits or get into a wholesale redesign of the lighting, replacing fixtures and so on.
Yeah,
There's been a contract that was approved, and we were walking through last week with John Sinagra, the building manager, and he's saying that for a variety of reasons, the final approval didn't come on the whole LED package, but they have that in the works. There's been studies done, I believe. We just haven't gone forward on it yet.
do you know whether it's fixture or just lamps?
I don't, but we will dig into that some more, Jeff, and we can get back to you if you like.
I think it's important for the three of you, since you have a contract with a client, to make sure that the client understands these things need to be integrated rather than separately awarded.
Yeah, well, that's been one of the discussions going on, and as you might guess, there's a lot of politics going on behind closed doors and a lot of different elements.
Actually, I think that's a really important comment, that this has to be integrated because the building was actually designed to, have everything integrated. That's the way, that was one of the big strengths of Coleman in his design approach, that everything has to be integrated. And so you can't just put drop ceilings in and stuff like that.
Look, I think, Henry, make use of the BSA's influence in reinforcing that topic with you. All right, and David, I don't know. David, are you the project manager for this, essentially for the group? You said something like that.
Yeah, I'm herding the cats. Yep.
Okay, well, look, that just keep in mind that you alone will not be able to have enough influence because you are already engaged, whereas maybe some group, and it could be, Bart, your engineering colleagues as well as the BSA, influencing the client or the client groups that are, they usually have their own fiefdoms or feel they have fiefdoms, and that is counterproductive for integration. I have a couple of questions which I have been remiss on asking. Is there, and this is from Ateli, is there a possibility to use a building mechanical control system to allow natural ventilation to occur on certain days that allow openings at bottom and at top? And how will this work for COVID issues? Well, Bart, you're getting a lot of engineering questions.
Yes. Well, one thing is that we typically have the ventilation systems made to take advantage of free air exchange. Whether we would do it directly up the light shafts or anything like that, I don't know. That would be, and you'd have to, one of the things that has to be really careful about building flushing type approaches and all, like night flushing, for example, is you've got to be sensing the humidity when you do that, because the temperature alone is not effective. You can create moisture issues. And the big thing that has happened in the last 10 or 15 years is building science has really come into the fore, and it was coming to the fore because of misunderstanding about moisture management. And so any of those kinds of things we've got to do very carefully. We are going to be looking at a bunch of air movement questions, and we're not going to be able to not look at it with this giant atrium that we're going to close. We're going to have stratification issues to consider, so we're going to have to address that. We're not there yet. We're at the beginning of that. So,
as well as fire and smoke and keeping out issues.
Look, one other resource that I'd like everybody to know about is the Society of Building Systems Educators. They are a group of teachers in various architecture schools who deal with building systems, and they look at the details in the way that Bart and his colleagues have to. Mark that down, SBSE, and look it up, because they are incredibly helpful in whenever somebody has a question. They a whole bunch of answers come from their colleagues, and they are a real resource for everybody who's in this design realm.
Great. Thank you, Peter.
Okay. There was one other question, but that's basically, you've already answered that, Bart. Attenuated window controls, you know, I'm sure that you're addressing all of those.
The buildings actually does have operable windows, we discovered, but they're on.
Hey.
Yeah.
Hey.
they're dangerously operable.
Right.
Yeah, let me say they were pivot windows that were taped shut with black tape.
Yeah.
It was really, it blended right into the frame, so we didn't notice it at first. But then I noticed that one was slightly ajar. When I went to move it, I realized that there was like angle brackets on the corners holding the sash together. So I said, "Don't open it."
Oh dear. All right.
Thank you for having us, Peter. This has been fun. And
Well, it's been extremely informative. Thank you all for all the very detailed work that you're putting in. Good luck on the rest of the year at the BAC, and I hope that maybe you'll get a chance to do this at ABX.
yeah,
Good.
we'll follow up. It'd be great. Thank you all for joining us.
Just
Thank
one
you
last
all.
thing.
Yeah,
One last thing.
Art.
One last thing before I go. My company name is Bales Energy Associates. We're not listed as BEA anywhere. So Bales Energy Associates, and we've got a website and everything. So
Good.
okay.
Thank everybody for attending. I am blown away by the number of people. We've never had such a large group come to our SBSE meetings, but this one was a blowout success.
Thank you, Peter. Thank you all for coming.
Thank
Bye-bye.
you, Peter.
Thank you.
This is
Bye-bye.
going
Thank you.
on the website. It's recorded.
Great.
Bye.
Bye-bye.